Pro Electrician, number 8. Overcurrent Protection. Technical terms and objectives are shown here on the screen. Overcurrent protection limits the current passing through a conductor, preventing high temperatures that could damage insulation. Consequently, the equipment connected to the circuit is protected as well. This chapter examines the causes of overcurrent and protection methods. Overcurrent. There are basic overcurrent protection requirements. All electrical circuits are required to be protected against overcurrent. Section 240.4 of the code specifically mandates that conductors be protected against overcurrent. The overcurrent device must automatically open the circuit when the current reaches a specified dangerous level. Fuses and circuit breakers are used as protection devices. The symbols used on schematic drawings to represent fuses and circuit breakers are illustrated on 8-3, shown on the screen now. Other devices, such as thermal relays and thermal cutouts, are sometimes added. Overcurrent devices must have correct voltage settings for the circuit served and must be marked with their maximum current interrupting capacity. Section 240.6 of the code lists standard current ratings for fuses and circuit breakers. These standard ratings are listed on figure -4, shown on the screen now. Warning: in order for an overcurrent device to function properly, it must be correctly selected and correctly located in the circuit. The overcurrent device must be operated in a safe manner, both electrically and mechanically, to protect the equipment and prevent harm to personnel operating the equipment. Overcurrent devices are placed in a system so that only the section of the system where the overcurrent exists will be opened. Other circuits originating from the same power panel do not suffer a power loss from a remote fault. Overcurrent device sizing factors. When sizing overcurrent devices, the required size often does not correspond to one of the standard sizes. For circuits less than or equal to 800 amps, the next higher standard size of overcurrent protection can be used if the conditions in section 240.4b are met. In circuits exceeding 800 amps, the required size or the next lower standard size of overcurrent protection must be used. Overcurrent device location. The concise rules for locating overcurrent devices, both within the circuits and on the premises, are stated in sections 240.15, 240.21, and 240.24 of the code. Ungrounded hot circuit conductors have overcurrent protection at the point of supply. Overcurrent devices must be readily accessible, free from physical damage, installed in an enclosure, or be otherwise protected and away from flammable material. The movable parts of an overcurrent device, such as handles or power actuated mechanisms, are guarded to protect personnel. Typically, branch circuit overcurrent devices are located at the power panel. For this, see figure 8-5 shown on the screen. There are some exceptions to this practice. Provisions listed in section 240.21 of the code are and referred to as the tap rules allow conductors, under certain restricted conditions, to be tapped without overcurrent protection at the connection point. These modifications are discussed later in the chapter. Note: feeder conductor protection is located before the service drop or service lateral, or on the primary side of the transformer. NEC Note 240.8: individual fuses, circuit breakers, or combinations thereof shall not be connected in parallel unless they are factory assembled in parallel and listed as a unit. Overcurrent protection devices. There are two types of devices used to protect circuits from overcurrent: fuses and circuit breakers. Fuses contain elements that melt under overcurrent load. When the element melts, it breaks the circuit, preventing the flow of electricity. After the cause of the overcurrent is located and corrected, the blown fuse is replaced with a new one. Circuit breakers are mechanical devices that open the circuit when an overcurrent is detected. These devices can be reset after being tripped, making them more convenient than fuses. Voltage rating. Overcurrent protective devices are rated for voltage and should be used in appropriate circuits. That is, the voltage rating of a fuse should be equal to or slightly higher than the current rating, but never lower. The table in figure 8-6 lists the maximum voltage ratings of various types of overcurrent protective devices. Ampere rating. Every overcurrent protective device has a specific ampere rating. Usually the ampere rating of a device is chosen based on the type of circuit and loads on the circuits, as well as code requirements. The ampere rating should be the same as the current carrying capacity of the circuit conductor. But there are exceptions, as with motors, where it is necessary to use higher ampere rated fuses. Overcurrent protective devices also have an interrupting rating. This rating is the highest fault current the device is intended to interrupt at its rated voltage. Fuses have an interrupt rating of 10,000 amps unless otherwise marked. Fuses with higher interrupting ratings are called high interrupting rated fuses. Circuit breakers have an uninterrupting rating of 5,000 amps unless otherwise marked. Fuses. Fuses are highly reliable and safe overcurrent devices. They consist of a resistance-sensitive link encapsulated in a tube. The ends of the fuse are connected to contact terminals of the conductor. The link has a very low resistance. If high current occurs, the link melts and opens the circuit. Two general types of fuses are available, plug and cartridge. Within these two types, fuses can be further classified as the following, shown on the left side of your screen: single element or dual element, fast acting or time delay, renewable or non-renewable. Single element fuses have a single element of one or more links that quickly melts in response to an overcurrent. The link melts at approximately 3 seconds at 200% overload current, and usually within thousandths of a second, less than half a cycle of an alternating current, for short circuit and ground faults. Since these fuses act rapidly, they are only used in circuits with no transient surge currents or temporary overloads. Figure 8-7, shown on the screen right side, illustrates a fuse melting and opening a circuit. Dual element fuses have two elements arranged in series. One element is similar to the element in a single element fuse and performs the same function. The other element is designed to allow for low-level overloads of about 5 times the ampere rating for over 10 seconds. This type of fuse is particularly useful in protecting a circuit where temporary surges are normal. A dual element fuse is shown in figure 8-8, shown on the screen now. These fuses are marked with a D. A time delay fuse or time delay feature is inherent in dual element fuses. However, not all time delay fuses are dual element. The main feature of time delay fuses, regardless of number of elements, is that they allow for momentary overloads. In renewable fuses, the fuse link can be replaced. This allows the fuse holder to be reused, reducing cost. A non-renewable fuse, one-time fuse, must be discarded after use and can be replaced with a new fuse. Current limiting fuses quickly open the circuit when a specified overcurrent is reached. These fuses clear the circuit of currents in a fraction of a second. Plug fuses. Plug fuses are available in two varieties, Edison base and type S. Figure 8-9 shows some of these. Plug fuses have a maximum rating of 30 amps. Fuses rated as 15 amps or less have a hexagonal window, while higher rated fuses have a circular window. Figure 8-10. Plug fuses are limited by the following voltage restrictions: maximum of 125 volts between conductors, or maximum of 150 volts between grounded and ungrounded conductors, or ungrounded conductors and the ground in grounded neutral systems. Edison based fuses are interchangeable. Fuses of greater current rating can be used in circuits of lesser capacities. This potentially dangerous oversizing problem is eliminated by using a type S fuse, which uses a screw shell adapter. The type S fuses must be used on all new installations and for replacement installations. There are 3 classifications of type S fuses with specific adapters based on their amperage ratings, or ampere ratings of 0 to 15 amps, 16 to 20 amps, and 21 to 30 amps. The appearance of a blown fuse identifies the type of overcurrent that occurred. An overload causes the fusible link to nearly melt, while the high currents associated with a short circuit vaporize the link and leave residue on the glass. For this, see figure 8-11. Cartridge fuses. Cartridge fuses are used in fused systems over 120 volts or 30 amps. There are two types of cartridge fuse connections: ferrule type and knife blade type. For this, see figure 8-12. Underwriters Laboratories, or UL, classifies different types of cartridge fuses. Most types have unique dimensions. This prevents one class from being replaced by another class in a circuit. Some of the most common types include the following. As seen on the screen, Class H. These fuses can be renewable or non-renewable. The non-renewable types can be time delay. They have a low interrupting rating of only 10,000 amperes and are not current limiting. The low interrupting rating restricts their use in new construction. Class J. Class J fuses are non-renewable and current limiting with an interrupting rating of 200,000 amperes. They are smaller than Class H fuses and are not interchangeable with any other class. They are rated for 600 volts and up to 600 amperes. Again, 600 volts and up to 600 amperes. These fuses have no time delay. A new cube style of Class J fuses is also available, shown on figure 8-13. Class R, these are non-renewable current limiting fuses with an interrupting rating of 200,000 amperes. These fuses have a rejection feature, so no other type of fuse can be installed in the same fuse holder. They may be used as replacements for Class H fuses and are rated for 250 volts and 600 volts and up to 600 amperes. Class T, a non-renewable current limiting fuse with an interrupting rating of 200,000 amperes. There is no time delay with Class T fuses. They are not interchangeable with any other fuse and are rated at 300 volts and 600 volts and up to 1200 amperes. Again, 1200 amperes. NEC note 240.6b, the rating of adjustable trip circuit breakers having external means for adjusting the current setting, long time pickup setting, not meeting the requirements of 240.6c shall be the maximum setting possible. Circuit breakers. Circuit breakers are permitted to serve not only as overcurrent protection device, but also as a disconnecting switch. They are often operated mechanically. They are often operated electrically or pneumatically, but must also be capable of manual operation. Circuit breakers must be marked to show if they are on or off. This indicates if the circuit is closed or open, respectively. There are two types of circuit breakers. The instantaneous trip circuit breaker. As its name indicates, this circuit breaker opens the circuit instantly when its interrupting rating is reached. It serves the same purpose as a non-delay current limiting fuse. See figure 8-14 shown on the screen. The second type of circuit breaker is the inverse time circuit breaker. Like a dual element fuse, this circuit breaker has two mechanisms for sensing overloads. The mechanism allows for a certain amount of overload to occur. The other opens the circuit at default level current. An inverse time circuit breaker will allow as much as 10 times the overload current prior to opening the circuit. Figure 8-15 shown on the screen illustrates the internal features common to most circuit breakers. Circuit breaker. Circuit breakers, like fuses, have standard interrupting ratings. These interrupting ratings must be clearly marked along with the intended voltage rating on each circuit breaker. Breakers of different interrupting ratings and voltages are constructed with different mounting features so that they are not interchangeable. NEC note 240.83c. Every circuit breaker having an interrupting rating of other than 5000 amperes shall have its interrupting rating shown on the circuit breaker. Conductor taps. Conductors normally have overcurrent protection at their point of supply. In the case of tapped conductors, conductors that are connected to another conductor, this additional protection is not required as long as certain conditions are met. These conditions are listed in section 240.21 of the code. Section 240.21b1, referred to as the 10-foot tap rule, allows a feeder conductor of smaller ampacity to be tapped without protection at the point of tap to the secondary side of a transformer, provided the tap does not exceed 10 feet in length, and it also meets the following conditions. For this, see figure 8-16. First condition is that the tap conductors must have a sufficient current rating to supply its loads. The current rating also must be greater than the rating of the overcurrent device at its termination point. The tap conductors must terminate at the device, panel board, transformer, or switchboard that it supplies. The tap conductors must be enclosed in a raceway between the point of tap and its destination point. Section 240.21b2, the 25-foot tap rule, permits taps less than 25 foot long without overcurrent protection at the point of supply as long as the following conditions are met, shown on figure 8-17. First is that the tap conductors and the overcurrent protection device located at their terminations are rated at a minimum of 1/3 of the ampacity rating of the feeder's overcurrent protection device. Second condition is that the tap conductors are enclosed in a raceway for protection. Third condition is that the tap conductors must terminate at an overcurrent device that is rated to the ampacity of the tap conductors. Section 240.21b4 allows for an unprotected tap of up to 100 foot long in high bay manufacturing buildings with walls over 35 feet high. These systems must be maintained and supervised by qualified individuals. See figure 8-18. In addition, the following rules apply. The tap conductors must not travel over 25 foot horizontally from the point at which the tap is made, and the total tap conductor length must not exceed 100 feet. Secondly, the tap conductor ampacity must be at least 1/3 of the ampacity rating of the feeder's overcurrent protective device. Third, the tap conductor must terminate at an overcurrent device that is rated to the proper ampacity. Fourth, the tap must be physically protected, installed in a raceway. And fifth, the tap conductors may not be spliced. Other conditions apply. The tap conductors must be 6 AWG copper or 4 AWG aluminum or larger. The tap conductors may not pass through ceiling, floors, or walls. And finally, the point at which the tap is made must be at least 30 foot above the finished floor of the building. These are the review questions for the chapter. Do go through these answers. Make sure that you are familiar with them. If not, do review this section, this lesson, by rewinding the video or going through the text. Here are the questions or problems for using the NEC section of the lesson. Again, these are based on the 2011 NEC. You may be using a later version by now, which is no problem at all. The sections and articles are very similar, if not the same, as the ones shown here. The point of this is for you to become familiar looking for information, finding information in the NEC, whatever version you may be using. And as you work these problems, you will become more and more efficient and knowledgeable on finding and knowing the information within the NEC, which is critical in the electrical professional electrician field. Do pause the video if you need to, and or rewind to review any of the sections included in this lesson. You have reached the end of this chapter or lesson. I do encourage you to look for the next lesson, and good luck with the rest of your studies. Thank you.